In this video, we're going to learn how to identify a few different positively charged aqueous ions based on the colours of their solutions and how they react with sodium hydroxide and ammonium hydroxide solutions. We'll also look at a special test just for the ammonium cation. We'll only be looking at some of the most common ions you might find in solution in the lab. There are, of course, many more cations than this, but this selection shows an interesting range of responses. If you use your detective skills, you may be able to figure out which one of these there is in a particular solution. Now, let's meet the ions. First, we have the aluminum ion with a charge of 3+. Next, we have the calcium ion with a charge of 2+. Then there's the chromium 3 ion with a charge of 3+. And two different types of iron, iron 2 and iron 3, with charges of 2+ and 3+ respectively. Next, the copper 2 ion with a charge of 2+. And the last of our metal cations, zinc 2+. We'll also look at the ammonium ion, NH4+. Of course, to have any of these in solution, we must be dealing with a dissolved ionic compound. This means if we have some of these positively charged cations, we're going to need some anions, which are negatively charged. For instance, chloride or nitrate anions. For this video, I'm going to assume we're dealing with the chloride salts of all these cations. The chlorides are all soluble in water, or at least slightly soluble. We'll start off by looking at each ion individually, and then we'll compare them. But before that, let's have a look at the tests. The tests we'll be using are the colour of the solution of the ions, although we'll be focusing more on the results of the chemical tests. Our first chemical test will be treatment with sodium hydroxide solution, first in dilute form and then to excess. The metal cations we'll be looking at will produce precipitates when treated with dilute sodium hydroxide solution. Some of these precipitates will then disappear if treated with an excess. And our second chemical test involves treatment with first dilute ammonium hydroxide and then an excess. Some of the ions respond differently to ammonium hydroxide solution than sodium hydroxide solution, allowing us to distinguish one from another. There will also be a special test for the ammonium ion, which we'll come to later. In the lab, you may come across sodium hydroxide in various forms. For instance, as a white powder or pellets, or as a clear, colourless solution. Ammonium hydroxide looks like this. It's also a clear, colourless solution. If you add ammonia, NH3, to water, you'll produce ammonium hydroxide. Sometimes you'll see ammonia solution, ammonium hydroxide, or ammonium hydroxide solution. These all refer to the same thing. Meanwhile, the term dilute is a relative term. However, with sodium hydroxide solution or ammonium hydroxide solution, you might be looking at a concentration of about 0.1 molar, while a concentrated solution may have a concentration of 1 or more molar. If we used a concentrated solution rather than a dilute solution, we might jump directly to the results of the excess test. Nonetheless, be wary that these concentrations are just guidelines. The results of these tests will depend on the amounts added and the concentration of cation in solution. Now it's time to move on to our first candidate. A solution of aluminum chloride will be clear and colourless. If we have a solution that contains Al3+ ions and we add dilute sodium hydroxide solution, we'll produce a white precipitate of AlOH3, aluminum hydroxide. But something slightly different happens when we add an excess of a sodium hydroxide. If there's enough sodium hydroxide in the solution, the aluminum hydroxide precipitate will react further and disappear. In this video, we won't be looking at the nature of the products involved when precipitates redissolve. What we're focusing on here is the pattern of precipitates and their colour. Now let's start with a fresh test tube of our solution and do the next test. If we add a dilute solution of ammonium hydroxide to a solution containing Al3+ ions, we'll form the same white precipitate of aluminum hydroxide we formed with sodium hydroxide. Just like a sodium hydroxide solution, ammonium hydroxide acts as a source of the hydroxide ion. However, if you add an excess of ammonium hydroxide or concentrated ammonium hydroxide, the precipitate will not redissolve. Again, we're not going to go into the reasons for this, we just have to remember it. In both chemical tests, hydroxide ions have been added to the aluminum ions, forming a precipitate of aluminum hydroxide. The hydroxide anion only has a charge of 1-, so we need 3 of them to counterbalance the aluminum's 3+ charge. So here is our balanced ionic equation. And we need to add in state symbols, taking care to include the solid symbol for our precipitate. Now that we've done one cation, we can go through the others more quickly. Here's everything we need to fill in for the next ion, which is calcium 2+. A fresh solution of calcium chloride is clear and colourless. Treating a solution of calcium 2+ ions with dilute sodium hydroxide will produce a white precipitate of calcium hydroxide. Adding an excess will not affect the precipitate, it will not redissolve. On the other hand, adding ammonium hydroxide solution to a solution of calcium 2+ ions will not produce a precipitate in the first place. Adding an excess will have no extra effect. Unlike aluminum ions, calcium ions only have a charge of 2+, so we only need 2 hydroxide ions to balance the charges. Next up is chromium 3. A solution of chromium 3 chloride will be a dark green, although it's only slightly soluble. Adding dilute sodium hydroxide solution to a solution of chromium 3+ ions will produce a grey-green precipitate of chromium 3 hydroxide. Adding an excess of sodium hydroxide solution will cause the grey-green precipitate to disappear. If we use dilute ammonium hydroxide instead, we'll produce the same grey-green precipitate of chromium 3 hydroxide. But adding an excess will have no effect, and the precipitate will remain. Since chromium 3 ions have a charge of 3+, we end up with a formula of CrOH3 for the hydroxide. Next we have iron 2, Fe2+. Solutions of iron 2 chloride are green. Adding dilute sodium hydroxide solution to a solution of Fe2+ will produce a pale green precipitate of iron 2 hydroxide. But adding an excess will have no further effect. Adding dilute ammonium hydroxide solution produces the same pale green precipitate, with an excess also having no further effect. As with calcium, we'll only need 2 hydroxide ions per Fe2+ ion to balance the charges. The next candidate, Fe3+, exhibits very different colours to Fe2+, so pay careful attention to the differences. Instead of being green, a solution of iron 3 chloride is yellow or brown. The result of the test with dilute sodium hydroxide solution is a red-brown precipitate of iron 3 hydroxide, with an excess producing no further effect. Adding dilute ammonium hydroxide produces the same red-brown precipitate of iron 3 hydroxide, and an excess has no further effect. So we see the same pattern of precipitations with iron 2 and iron 3, but very different colours. As with aluminum and chromium 3, we need 3 hydroxide ions to balance the charge of Fe3+, giving us FeOH3. Next, we'll look at copper 2. Solutions of copper 2 chloride are blue. Adding dilute sodium hydroxide solution to a solution of copper 2+ will produce a pale blue precipitate of copper 2 hydroxide, and an excess will have no further effect. Adding dilute ammonium hydroxide instead will produce the same pale blue precipitate of copper 2 hydroxide. However, in an excess of ammonium hydroxide, the precipitate reacts, dissolves, and the solution turns a darker blue. Our ionic equation for the production of the initial precipitate is simply Cu2 plus 2OH- react to form CuOH2. Again, we're not going to focus on the nature of the product when the precipitate dissolves. Next up, we have the last of our metal cations. Solutions of zinc chloride are colourless. Adding a dilute solution of sodium hydroxide to a solution of Zn2+ ions will produce a white precipitate of zinc hydroxide. With excess sodium hydroxide solution, the precipitate will react and dissolve. We get exactly the same result with ammonium hydroxide solution and excess ammonium hydroxide solution, with the white precipitate of zinc hydroxide dissolving in excess ammonium hydroxide. And in our balanced ionic equation, the zinc 2+ ions and OH- ions are in a ratio of 1 to 2. Now let's move on to the only non-metal cation in this video. Ammonium chloride forms colourless solutions. We can begin to detect ammonium ions by adding sodium hydroxide, either in solid or solution form. What happens is essentially an acid-base reaction, where the acidic ammonium ion reacts with the basic hydroxide ion, producing ammonia gas and liquid water. You may see bubbles produced, but ammonia doesn't have a colour, so how do we know it's ammonia? The most obvious way is via the smell, because the smell of ammonia is very distinctive. However, if you have the option, you should not inhale ammonia. Instead, the best option is to check whether the gas is basic, using wet red litmus paper. If the gas is ammonia, the ammonia will dissolve into the water, turning the red litmus paper blue. In some cases, you may need to provide some heat to produce enough ammonia for the test. Now that's all the ions we're going to look at in this video. Let's look at them all at once. Here are the cations, and here are the tests. I've isolated ammonium for now. If we get a precipitate for a particular test, we'll put a tick, otherwise we'll put a cross. For all the metal ions in this video, we get a precipitate when we treat their solutions with dilute sodium hydroxide solution. For aluminum, calcium and zinc, the precipitate is white, while the precipitates for chromium 3, iron 2, iron 3 and copper 2 are all different colours. For the aluminum, chromium 3 and zinc ions, adding an excess of sodium hydroxide will cause the precipitate to dissolve. For the rest, adding more sodium hydroxide solution does not affect the precipitates. If, instead of using sodium hydroxide solution, we use ammonium hydroxide solution, we get exactly the same results for all the ions with dilute ammonium hydroxide, apart from with calcium, where we don't get a precipitate at all. And there's still no precipitate if we add an excess. For copper 2 and zinc ions, when we add an excess of ammonium hydroxide, the precipitate will react and redissolve. In the case of the copper 2 ions, the solution will turn a much darker blue than before. For the remaining metal ions, adding an excess of ammonium hydroxide will have no further effect on the precipitate. And finally, for the ammonium ion, all we need to do is add sodium hydroxide and a little heat. We can then treat any gas given off with wet red litmus paper, which should turn blue. After all that, it's time for some practice. Which of the following metal cations does not produce a precipitate when a few drops of aqueous ammonia are added to a salt or solution of that metal cation? A. Zn2+, B. Al3+, C. Ca2+, D. Cr3+, or E. Cu2+. The question describes these 5 options as metal cations. We are dealing with cations of zinc, aluminum, calcium, chromium, and copper. And we're being asked which of these metal cations, as a salt or in solution, would not respond to aqueous ammonia and produce a precipitate. The formula for ammonia is NH3. Ammonia can react with water to produce ammonium hydroxide, a good source of the hydroxide ion. The question doesn't tell us directly if the ammonium hydroxide is dilute to an excess or concentrated, but since it's only a few drops, we can safely assume it's dilute. The question is, what is going to happen when we treat each of these ions with dilute aqueous ammonia? Zn2+ ions will react to produce a white precipitate of zinc hydroxide. And we get a similar reaction with Al3+ ions, producing aluminum hydroxide. However, Calcium 2+ ions do not react with aqueous ammonium hydroxide, no matter the concentration. There isn't an easy way to understand why, you'll just need to remember it. Meanwhile, chromium 3 ions do react, forming a grey-green precipitate of chromium 3 hydroxide, while the precipitate we get from copper 2+ is pale blue copper 2 hydroxide. Now, there is one possible point of confusion with this question if we're not quite sure if we're dealing with dilute or excess ammonium hydroxide. In excess ammonium hydroxide, the precipitates formed from Zn2+ and Cu2+ ions dissolve. But since we are only dealing with a few drops, we can be fairly confident that we are dealing with dilute conditions. Therefore, out of the 5 options, the only metal cation that does not produce a precipitate when treated with a few drops of aqueous ammonia is calcium 2+. Now, let's finish up with the key points. Different cations can be detected based on the precipitates they do or do not form. And these are the ions and tests we've looked at. These are the colours of the precipitates we get when we treat each of these ions with dilute sodium hydroxide solution. If we treat these with excess sodium hydroxide solution, the precipitates for aluminum 3+, chromium 3+, and zinc 2+ will redissolve. If instead of using dilute sodium hydroxide we use dilute ammonium hydroxide instead, otherwise known as aqueous ammonia, we get exactly the same precipitates apart from calcium, where we don't get a precipitate at all. If we continue to treat with ammonium hydroxide to the point of excess, the precipitates for copper 2+ and zinc 2+ redissolve. The rest stay as they were. And the last cation, ammonium, can be detected by treatment with sodium hydroxide and potentially a little heat. We can smell the ammonia gas given off or detect it using wet red litmus paper, which should turn blue.